Okay, so this is the second piece of the lecture for Monday, September 11th. We are picking up from where we left off, and what we talked about was Fourier series. We're thinking generally about transformations. Right now we're transforming deterministic functions, so there's nothing random yet. And in particular we focused on transforming a periodic function. And when a function is periodic, it makes sense to transform it in terms of sines and cosines, because the sines and cosines are periodic, and what we've seen is that if I begin with a periodic function, then it can be transformed into just coefficients, giving the amplitudes of the corresponding frequencies of the sines and cosines. And nicely, because the function we start with is periodic, the frequencies of the sines and cosines we need to include is discrete. And so that's why we're able to recode our original function in terms of these coefficients. So we're going to continue on with this with Fourier series for another couple of slides. We're going to look at this frequency stuff a little bit more, and what we can kind of think of is that this is providing some a little bit more interpretation of what's going on. We'll then talk about Fourier transforms, where we will still do a Fourier transformation. There still will be a frequency interpretation, but we'll be applying it to a non-periodic function, and so it's a little bit harder to see the frequencies, and the frequencies are no longer going to be discrete, but we'll make that jump here in a couple of slides. So picking up where we left off, if you want to follow along in the book, please do read Schabenberger and Gotway, page 63 is about where we're at. So what Schabenberger and Gotway do is they define the energy of a periodic function f with period 2p in the interval from negative p to p to be given by this quantity here. Okay, so if we have a periodic function with period 2p, we know that if I look in the window between negative p and p, I get the entire information about the function. And so they call this quantity the energy, which kind of makes sense. We can think about two different periodic functions. So I'm going to think of kind of this simple function like this. It's periodic, so it would extend off in both directions and would repeat. Here's another periodic function with a bit more going on. Let's say it's got, kind of a big wave here at the start, and then maybe a little wave, and then a medium-sized wave. But if this were to repeat, so just imagine copying that crazy wave I've got there between negative p and p and replicating it, it would be a periodic function, and you would say, gosh, this second function has a lot more going on. And one way of trying to quantify that would be by looking at the energy. If we took the values of this function, squared them so that all the negative values became positive, but also the large values got a magnitude by their squares, we would get a larger number associated with this second function than we would for this first function. And so that's going to be the definition of energy.